Welcome to This Explainer. Today, we are unpacking the incredible, frankly mind-blowing mechanics of our home planet. We're going to break down the exact, precise movements that shape our days, our years, and our seasons. It's so easy to just take the ground beneath our feet for granted, but as you'll see, Earth is a highly dynamic, perfectly calibrated system that's literally in constant motion.
Okay, let's just quickly map out our journey today. We've got 6 parts. 1, the grand cosmic illusion. 2, rotation, the daily spin. 3, the magic of the tilt. 4, revolution, the yearly orbit. 5, solstices, equinoxes, and seasons. And finally, 6, a perfectly balanced planet.
Section 1, the grand cosmic illusion. So think about this for a second. Do you actually feel like you're moving right now? Probably not, right? When we look up at the sky, it really looks like the sun is the one moving across the horizon, traveling right over us while we just stand totally still. But honestly, that's just the grand cosmic illusion. The reality? We're the ones moving. And we are moving at absolutely mind-boggling speeds.
The sheer scale of the speeds we're talking about here is just astonishing. Looking at these numbers from our sources, the Earth is rotating at 0.5 kilometers per second. To put that into perspective for you, that is significantly faster than a Formula One race car at absolute top speed. And it gets crazier. Add to that our revolution around the sun at 30 kilometers per second, and our entire solar system tearing through the galaxy at 250 kilometers per second. Yet, because this motion is so incredibly smooth and constant, we don't feel a single bump. Crazy, right?
Moving on to Section 2, rotation, the daily spin. So the Earth rotates on its axis from west to east, and it takes exactly 24 hours to complete one full spin. This elegantly simple movement perfectly explains the whole phenomenon of day and night. Because the Earth is a sphere, obviously, only one half of it can face the sun at any given moment. So the side facing the sun gets bathed in daylight, while the opposite side gets cast into the cold shadow of space, giving us night. You can actually visualize this brilliantly with a really simple activity from the text. Just picture taking a standard classroom globe and sticking markers on cities like New York, London, and Karachi. Now, darken the room and shine a flashlight directly at the equator. That's your sun. If you manually turn the globe from west to east, you literally get to watch those cities move out of the dark shadows and into the bright light. It simulates a perfect sunrise. Section 3, the magic of the tilt. Okay, before we go any further, we really need to precisely define our axis. The axis is basically an imaginary straight line running right through the dead center of the planet, securely connecting the North Pole at the top to the South Pole at the bottom. Think of it as the invisible rod that the Earth spins around. Now, think of a figure skater performing a spin on the ice. Normally, their body is perfectly straight up and down, right? A strict vertical axis? But our Earth does not spin upright like that skater. Actually, Earth's axis is permanently tilted at a very specific angle of 23.5 degrees. Lock that number in your brain, because that 23.5 degree tilt is literally the secret ingredient to life as we know it. Section 4, revolution, the yearly orbit. Now, while we're spinning continuously on that tilted axis, we're also traveling through space, making a massive circle around the sun. This movement is called a revolution, and the set, totally predictable path we follow is called an orbit. And hey, remember that speed chart from earlier? We are zooming along this orbital path at a blistering 30 kilometers every single second. So the really crucial point here is how long this monumental journey actually takes. To complete one full revolution around the sun, the Earth takes exactly 365.25 days. Now, you might be thinking, wait a minute, my calendar only has 365 days. And you'd be absolutely right. Because a standard calendar year rounds down to 365 days, we are left with a quarter of a day left over every single year. So what do? We simply collect that extra 0.25 mathematically over 4 consecutive years. A quarter times 4 equals 1 whole. So every 4 years, we take that accumulated full day and stick it right at the end of February, giving it 29 days instead of 28. And boom, that is the exact mathematical reason we have leap years. Section 5, solstices, equinoxes, and seasons. To understand seasons, we first have to understand how sunlight hits a sphere. Comparing direct and indirect sunlight perfectly demonstrates the huge difference between the boiling hot equator and the freezing cold poles.
If direct sunlight hits a surface straight on, the heat is highly concentrated in one spot. Just imagine that poor melting snowman. But when sunlight hits the curved poles, it comes in at an angle. It's indirect. The exact same amount of energy is forced to spread out over a much larger surface area, which makes it far less intense and much, much cooler.
So let's look at the Earth's orbit with that magic 23.5-degree tilt locked in place. As we revolve around the sun, the hemisphere that is physically leaning towards the sun gets all that intense, direct heat. That gives them summer. But then 6 months later, when the Earth is on the exact opposite side of the sun, that same hemisphere is now leaning away, so it receives weaker, angled, indirect sunlight, completely plunging it into winter.
These mechanics build our entire calendar year around 4 critical milestones. We have 2 solstices, June 21st and December 21st. The summer solstice marks the absolute longest day of the year, which happens when a hemisphere is tilted closest to the sun. The winter solstice, that's the shortest day. Now, right in between these extremes, we hit the equinoxes, around March 21st and September 23rd. The word equinox literally translates to equal night. Why? Because on these 2 specific days, neither pole is tilting toward the sun, meaning both hemispheres get strictly equal amounts of daylight and darkness.
And you know, the extreme nature of this planetary tilt even creates some of the most breathtaking natural phenomena on Earth. Take the midnight sun, for example. Because the poles tilt so far toward the sun during their respective summers, locations way up north, like Norway, Sweden, and Finland, experience days where the sun literally doesn't set. If the weather is clear, you can stand on a cliff and stare right at the sun shining brightly at exactly midnight. No way, right? It's incredible.
Section 6. A perfectly balanced planet.
Comparing these 2 movements perfectly summarizes everything you need to take away from this explainer. On one side, we have rotation. That's Earth spinning like a top from west to east every 24 hours, giving us our daily cycle of day and night. On the other side, we have revolution. That's us zooming around the sun every 365.25 days, which, when you combine it with our permanent 23.5-degree tilt, gifts us our dynamic, ever-changing seasons.
There's a quote directly from our source text that says, "If the Earth was to remain stationary, there will be no day or night, nor will there be different seasons." And that is such a powerful reminder of why all this actually matters. The very rhythm of life on Earth, from the warmth of the daylight to the agricultural cycles that rely on predictable weather patterns, completely depends on this constant, beautifully balanced mechanical motion. Without it, one side of Earth would just burn, the other side would freeze solid, and life as we know it would entirely cease to exist. Our planet is just incredibly special. Knowing how mathematically fragile this perfect balance really is, I'm going to leave you with a provocative thought to ponder as you go about your day. Imagine looking up at the sky, fully knowing the massive speeds we are traveling at right now. How completely and radically would your entire world, your climates, and your everyday life change if our 23.5-degree planetary tilt just suddenly vanished and we straightened out exactly like that upright figure skater? Think about it. Thanks for joining this explainer, and keep questioning the incredible mechanics of our universe.